The infinite data ocean is real. To date, we have created 60 billion terabytes of data. If we continue this data growth path, this immense volume will triple in size in just 3 years' time. How do we make sense of all this data and apply it for our common good? The answer can be found within our computational storage experience. The infinite data ocean is real. To date, we have created 60 billion terabytes of data. If 1 grain of rice is equivalent to 1 byte of data, it would take 60 Pacific Ocean-sized volumes to hold all of those bite-sized rice grains. If we continue this data growth path, this immense volume will triple in size in just 3 years' time. With an annualized 38% growth rate, edge devices are expected to generate 50% of all data created by 2025 and will demand distributed compute resources at the source of the data to meet application performance requirements. From data analytics to video streaming and AI inference, the data ocean continues to expand at an astounding rate. This is truly a paradigm shift in our evolving digital world. How do we make sense of all this data and apply it for our common good? The answer can be found within our computational storage experience. Our search and rescue mission is as follows: to provide the compute and storage resources to search through this massive data ocean and make timely decisions with urgency, accuracy, and consistency to deliver results that meet end-user expectations. Over the course of our mission, we will execute database searches, deliver on AI inference tactics, enable mission-critical decision-making, and exceed targeted application performance by offloading host processors. Today's compute, storage, and networking infrastructures, from on-premise to cloud data centers, undergo the following challenges. Latency. Stored data is transferred across a network to host servers for all required processing tasks, which introduces delays in achieving results. Restricted bandwidth. Network congestion and over-provisioned servers constrain available compute and networking resources. Expense. Cloud compute instances and on-premise equipment costs increase the total cost of solution ownership, or TCO. Security and privacy issues. Data is vulnerable when it is shared across networks and third-party compute resources. Resource interdependencies. Misbalanced provisioning of compute and storage resources and network bandwidth constraints may impede application performance. The computational storage resolution provides reduced latency. Computational storage brings compute resources to the data for improved response times in data analytics and management. CapEx and OpEx savings. By deploying compute resources at the data, less host server resources are required, which in turn decreases infrastructure costs. Security and privacy compliance. Localized data processing provides better protection and control of sensitive data pools. Flexibility and scalability. Computational storage resources are dynamically scaled and tailored to meet customer application requirements.
Hi, and welcome to this exciting forum. I tell you, I think one of the most important technological fields that I am working on today is the area of computational storage. We all know of the explosive growth that's happening in data. We all know that NAND flash has been revolutionary in helping us to be able to access that data much more quickly than we were able to before. And that is allowing us to be able to bring in data much better than we used to. It's much more accessible. But as the data continues to explode, we need to be able to make sense of that data. And making sense of that data means that we have to do processing with it. And even though computers and servers are continuing to increase in their core count, increase in their capability, it's still too much to ask the network and the processor to do all of that computation themselves. What's important is that we push some of those elements down to the storage itself, where it's closer to the data. Of course, we all call this computational storage. To me, this is the key thing that we need to really advance the fields of artificial intelligence and machine learning. By being able to distribute this, to have the processing or at least the filtering or pieces of the total job down closer to the data, we're going to be able then to make sense out of that data. We're going to be able to make the world a better place because we're going to be able to make advances in genomics and medicine that we had not made before. So please, during this conference, let's work together. Let's see what we can do to push computational storage to places that we didn't even think we could. It's an exciting time. It's an exciting time to be involved in storage, and especially in computational storage.
How is computational storage deployed? The left illustration shows a classic compute storage and networking architecture. The central processing unit is the control hub for compute task execution, DRAM memory, SSDs, and PCI Express accelerator cards. There are a number of challenges with this topology, from network congestion by large data transfers to the host, to processor overloading and system latencies. With computational storage, compute resources reside within each SSD, which can dramatically alleviate these issues. The right side illustration shows a computational storage architecture with the following benefits: CPU offload and reduced data movement to the host, low latency data movement across local compute resources, data processing within a secure drive environment, scalable compute and storage resources that improve application performance efficiencies. Here are some specific features of the Samsung Smart SSD computational storage product. 4 terabytes of vNAND flash storage, a Xilinx programmable FPGA compute accelerator, integrated DRAM within the FPGA and an assigned PCI Express address space to the host, a soft PCI Express switch that supports concurrent reads and write commands and peer-to-peer communications.
So cloud customers, they have a really big demand to process their data. And to more efficiently address this demand, the cloud providers for some time have been investigating ways of bringing compute closer to the storage. The computational storage improves the data center architecture to meet these needs by changing the balance between compute, storage, and networking. As a service, data center infrastructures need to be architected to support the growing application performance requirements across public, private clouds and to the edge. From cloud data centers with millions of solid-state drives to the exponential growth of distributed compute nodes and compute aggregation points, performance is no longer the only requirement. Data analytics require low-latency compute to support mission-critical applications and to make real-time decisions. Computational storage architectures can be designed for database functional offload, such as the Samsung Smart SSD, which alleviates processing tasks from the host processor complex while providing dense storage capacity. Additionally, it's possible to run the entire database on a computational storage device or across an array of devices by deploying an upcoming server and drive architecture as well. Flexibility in computational storage architectures, either at the component level with FPGA or ASIC, or by supporting different form factors with different thermal envelopes that support the increased compute performance, have utility across distributed compute and edge applications, for example, AI and video encoding. In summary, computational storage provides an exciting new approach to enabling more applications and solutions across the cloud to edge ecosystem.
Let's learn about computational storage in data analytics.
Netezza has a long history of implementing versions of computational storage. Our former architecture combined an HBA, a PCIe switch, and FPGA acceleration onto a single card connecting to a bunch of JBOD drives. The Samsung Smart SSD takes all these features and rolls them into a single device. We see a lot of potential in this approach, especially for our on-premise customers, where we want to provide cost efficiencies and performance optimizations, and also the cloud capabilities our customers demand. For database, data lake, and lakehouse, and other large-scale analytic workloads, pushing compute down to the storage saves in multiple ways. First, it saves in network demand. Filtering the storage allows the compute resources better quality of service among the database functions. Second, the compute nodes can be more sparse because their overhead is reduced, saving in cost even when we move workloads to the cloud. Finally, having the ability to move compute closer to the storage helps us build deeper data pipelines, allowing us for more queries in flight because we can better use the resources on the compute nodes and process data as fast as the storage can deliver it. This allows us to process the biggest queries our customers have.
Now let's look at computational storage in action across a number of use cases. With this Spark Acceleration TCO example, data throughput is increased without an additional server investment required. Here's the scenario. With a baseline of 1,000 servers, to increase the compute performance capacity by 25%, an additional 250 servers are required. Or by deploying computational storage with Samsung Smart SSDs and BigStream Spark Acceleration technology across just 1/3 of the existing server baseline, a TCO savings of 82% can be achieved with no changes required by the host software. In this Greenplum Postgres acceleration use case, the Smart SSD offloads scan-heavy queries from the CPU. Multiple scan engines are instanced in the Smart SSD with the Vitesse Postgres scan acceleration technology. The Greenplum data warehouse is scanned on demand with a budgeted 9x performance improvement in select TPC-H queries.
Computational storage is an exciting new technology that we've been exploring in VMware in the Office of the CTO. It brings compute directly onto the storage layer, allowing the resolution of complex data problems without the need to move data across the system bus or even between storage devices. Imagine a cluster of 24 NVMe compute devices that have both storage and compute in one device. VMware has a database called Greenplum, which is a parallel database built on Postgres, but which is able to divide data queries up among a range of devices. Normally, this would happen on a server cluster with 10 or more servers performing parallel data queries. With computational storage, this can happen inside of a 2U server spanning up to 24 NVMe devices in parallel. We've been able to show that we can solve complex graph problems, data pre-processing, and other types of problems that normally would require transfers of vast amounts of data across the system bus. Another area that we think this has strong potential is the convergence of both complex data analytics workloads and real-time control problems on the same server. Traditionally, you never combine bursty workloads with workloads that are in the critical control path. But by performing the data analytics directly on the storage layer, this can be combined with no impact to the main system CPU, which can be left to perform critical control path problems. A good example is the virtualization technology in power substations. So we're very excited to see how our customers will use computational storage to build sophisticated new intelligent edge solutions.
Here's another Smart SSD use case on high-performance object storage and the S3 Select service.
Hi, I am Mayank Saxena, Senior Director Engineering at MSL, Samsung. In this video, we are showcasing high-performance object storage, which enables the fast emerging use case and need of high-performing real-time analytics over large-scale object storage. HPS solution from Samsung has been mindfully architected with the customer use case in mind and utilizes the emerging concept of S3 Select. where data set of interest, that is, specific columns and chunks within them for a particular query, are processed versus the traditional way of transferring the complete data set to CPU. As you can see on the top right, various ML applications needing to serve real-time analytics utilizing S3 now have additional standard interface of S3 Select of HPOS, enabling applications to have data of interest chunked and stored in computational storage, where utilizing our computational SSD's acceleration capability to perform near data processing. Major benefits of HPOS: faster performing queries, higher throughput with lesser network traffic, lower TCO with reduced CPU usage, which we will now show you using the live demo setup.
In this demo, we will do a drag race between Amazon running S3 Select versus our HPOS server that was accelerated using computational storage. In the architecture slide, we see the S3 client sending a S3 Select request. This is processed using computational storage. In this drag race video, we will measure latency and throughput for both Amazon and HPOS solutions when executing S3 Select. For HPOS, we'll also measure CPU consumption over the duration of the run. In the next slide, we will analyze the results. Metrics gathered during the drag race show that the performance of HPOS was more than 5 times better in terms of latency and 6x better in terms of throughput, all the while consuming less than 0.5% of CPU, thereby improving TCO using computational storage. My name is Kedar Patwardhan. I work for MSL. Thanks for watching the video.
This is a smart SSD use case in video encoding. In this scenario, there is a video file workload requirement of 500,000 conversions per day. The compute capacity to support this workload requires 357 servers. However, by using Samsung Smart SSDs with CTXL video encoding acceleration technology, Smart SSDs can be deployed across 1/3 of this server baseline, providing a total cost of ownership savings of 55%. There are many emerging applications that may benefit from computational storage. One example could be searching a COVID-19 patient database for specific trends using numeric and inverse theoretic transforms. These algorithms consume a large portion of host processing resources. However, with Smart SSD, search performance can be improved by greater than 40%. A second example is cyber search, to determine and isolate security threats across large petabyte-sized databases. Normally, such methods can take up to days to perform. With an array of Smart SSDs, cyber search can be reduced to just minutes for improved performance and security protection. Let's listen to Dell fellow Walt O'Brien as he shares his vision for this very thing.
Most of today's IT workloads run on x86 CPUs. However, a growing percentage of IT workloads are taking advantage of silicon diversity. Specialized silicon like GPUs, TPUs, DPUs, and FPGAs to deliver faster results at lower cost using less energy than x86 CPUs. Emerging computational storage solutions like Samsung's Smart SSD use a type of specialized silicon to help customers tackle data-intense problems. To give an example, one of our customers is using Dell servers with Smart SSDs to produce a cyber forensic appliance. By programming an array of Smart SSDs to perform a search on its own content at near media read speeds and returning only matches, a huge computational and data movement burden is offloaded from the x86 CPUs. This enables a parallelized full content search of over a petabyte of non-indexed telemetry data for threats in minutes instead of hours or days required using traditional approaches and only x86 CPUs. Today, computational storage adoption is limited by the difficulty required to modify applications to use it. The future looks much brighter as dedicated technical working groups in both the SNIA and NVMe standards bodies hold the promise of making application integration easier and boosting adoption.
Another application is genomic sequencing. This is one of the largest data creation applications that may benefit from computational storage. Here is Professor Heiner Litz from the University of California at Santa Cruz on how computational storage will positively affect genomic sequencing research and related medical applications.
Storage devices continue to scale in capacity according to Moore's law, providing us with higher densities every year. Unfortunately, bandwidth and latency has not been scaling at the same rate. And that means that data communication between the host and the storage device has now become the main bottleneck. This is particularly true for applications in the genomics domain, which are highly challenging as they operate on terabyte or even petabyte sized footprints. And it is projected that genomics data is scaling 10x faster than Moore's law at exponential speed. So to address the problem of moving all that data back and forth between the host and the SSD, we've been looking at computational storage devices where particularly heavy compute portions are performed on the SSD itself. This is challenging because these genomics applications are highly complex. And they introduce a lot of special data formats that have to be resupported on the smart SSD. But nevertheless, the importance of the genomics revolution, which will really allow mankind to cure diseases like cancer and do individual treatments of patients, requires that new technology, and we believe smart SSDs are the optimal choice for achieving that goal.
We have experienced how computational storage will enable a mission-critical response for data analytics solutions, from database search to genomic sequencing. We have also seen how data security can be enhanced by bringing compute resources to the data, so the data can stay local. Computational storage provides new performance capabilities and efficiencies by offloading traditional host processors, alleviating data networking congestion, and by providing scalable compute and storage resources from cloud to edge applications. Samsung is proud to offer our leadership in computational storage solutions in partnership with Xilinx and their FPGA acceleration technology. Here are some final thoughts from Salil Rajay, General Manager of Xilinx's Data Center Group.
Hello, I'm Salil Rajay, Executive Vice President and General Manager of the Xilinx Data Center Group. We are very excited to partner with Samsung on smart SSD solutions. We've seen some great solutions today, and we hope you're as excited as we are about the possibilities of computational storage. Along with Samsung, we are looking forward to solving your business challenges. We invite you to share those challenges and opportunities with us.
I'd like to express my thanks to our industry experts and visionaries who have helped to define the computational storage opportunity. We have seen just a sample of use cases with Samsung Smart SSD. We invite you to experience computational storage with us and share your challenges and opportunities today.